Good evening. Let's try that again. Good evening. Hey, there are people in this room. You know, you folks just gave a warm round of applause, and for someone who has butterflies, even though I've been doing this sort of thing since 1995, you begin to tell them to settle down and get out of the way. So thank you for that warm round of applause. So let me get started because I have a limited time here, and I know you folks have lives outside of the Royal Institution. So I'm here to tell a story, and we're going to try to tell a very accessible, entertaining, and educational story. So let's get started. So most of you have never heard of me, so we're going to start with kind of questions that a lot of people ask, namely, what is the universe made of? And how does it work? So these are questions that, children ask, the ancient Greeks asked these things. And the ancient Greek starts to give us some kind of answers. Where do those answers come from? Well, let's see. Philosophers? Do philosophers actually go out and do experiments? Not generally. So this is one of the things about the evolution of science that is very important to understand, is that science comes out of a part of philosophy called natural philosophy, where individuals who were philosophers would spend time thinking about things, and just thinking, deliberating, discussing, and then there would be a distillation of ideas. And when a consensus was reached, that was considered the scientific standard. That's not what we do today, and we'll come back to talk about that later. So in answering these questions, I'm going to first show you this picture. How many of you saw this picture recently? Anybody in the audience? Nobody? Really? That's very interesting because this picture was shown worldwide because two scientists here in England at, Birmingham, performed an experiment recently. And this experiment resulted in the first image our species has ever seen based on an observation of what a photon looks like. That's a photon, according to this experiment in Birmingham. And that's, being here in Merry England, I thought it'd be great to show some of the locals what is still going on in science on this. But I thought it would be really nice to show you what the locals are still doing in science. Because this building, of course, is, in my mind, it's a temple to science. I had a wonderful tour earlier this evening, and we got a chance to walk through the exhibits, and I can verify that I just totally fanboyed out.
I can verify also.
Yes, I was a total fanboy walking through the exhibit. I was like, whoa, Michael's everywhere, right? And I'm not talking about Michael Jackson. And so I want to start with this picture. And so this picture is all over the web, it's on newspapers, and I looked at it and said, does anyone wonder why that looks like a starfish in a ring? That's what a photon looks like? Really? And so that's why I want to start my talk, just asking you this question. So let's see if we can figure out by the end of the talk, or it's actually about halfway through, why this is the case. So raises questions. Why should a photon look like starfish in a ring? So let's talk about me a little bit, because I want to do a little bit of an introduction biography. This is me. I was the valedictorian of my high school in 1969. I started dreaming at age 14 about this place. That's the Massachusetts Institute of Technology in Cambridge, Massachusetts. Although that was my dream, by the time I was 18, I was convinced I would never have the opportunity to go. Why? Because I'm an African American. And in my country, race determines opportunities for lots and lots of people. But in 1969, things started to change. And so I had the opportunity to go to my dream school. So you would think I was very happy, right? Because 4 years of hoping and wishing? No. It was the hardest thing I had ever done. You see, before that, school had never been a challenge for me, ever. I just wake up and, answers would appear, and I'd do tests and what have you. That's how you wind up being the valedictorian of your high school class, right? You get A's, and it's not really all that hard work for some of us. And so MIT was a challenge, and it took an emotional toll. That tear is not figurative. I spent nights weeping. And so I also understood that when there's a lot of negative emotion in one's life, you can't let that go. You should think of, I like to think of myself as there's two versions of me. There's the one that's doing the talking to you, and then there's a real me, my subconscious, the thing that determines whether I like green versus blue, whether I find one person attractive or another. That subconscious that we all have. So we come in dualities. And those emotions that you have are mostly not governed by this version of me, but by that other version. And you have to manage and take care of that other version if you're going to have a very pleasant life. And I understood this as a first-year student. And so I looked for a remedy. Don't laugh. A bowling ball. How can a bowling ball be a remedy to emotional pain? Well, when I would take tests, I would be extraordinarily nervous. And therefore, for the first 15 or 20 minutes, I would just be sitting there in stunned shock. Then I started writing. Now, of course, everybody else had an hour-long exam, but since my first 20 minutes was spent in shock, I only had a 40-minute long exam. And that meant that I never had scores on tests that looked like I was doing much of anything. That created tremendous frustration because at age 4, I told my father I wanted to be a scientist. And here it is, age 18, 19, I'm having this struggle. So the bowling ball was so I could learn to do something I hadn't done before and have success. And in fact, every time I would have a bad test, I would go to the bowling alley, which was on MIT's campus. And so I would have a bad test, I'd go to the bowling alley. I'd have another bad test, I would go to the bowling alley. This happened over and over and over again. And to show you how extraordinarily efficient I became at testing, by the time I left MIT, I was on the championship bowling team. That suggests I had lots of practice, which then implies I had lots of bad tests, right? But it's all true. So that's one thing about me. But in the second semester of my freshman year at MIT, Michael Faraday started to come to my rescue. And this is a very interesting thing for me to relate to. This is 1970. I'm in my first class on electromagnetism. This is a picture of the copy of the actual textbook that I used in 1969. I still have a lot of my college textbooks, so I took this picture for this audience to see. On page 226, you see the name Faraday. And that's the first time that I saw Michael Faraday's name, because it's in the chapter on electromagnetic induction. And so, why was Michael so important versus my first semester when I struggled with another native son called Isaac somebody? Is it Newton? Is that the guy I'm talking about? So another native son to the island. Why was Michael so much different? Well, it's because what Faraday and electromagnetism highlights is that an incredible tool to do theoretical physics is the use of visualization, which taps directly into one's imagination. So we saw pictures like this in the book, but I was also aware of the fact that these images could come alive. I could see them in my head. I could see them moving. And that's the thing that seems to have empowered Michael Faraday's powers of and ability to do world-class theoretical physics. So my imagination was now hooked into my physics in a way that it had never been before. Well, that's good because, you see, I'd spent part of my teenage years reading things like this, and great tomes like that, and encyclopedias like that. And so the use of the imagination was something I was very, very efficient with because, you see, my mother died when I was 11 years old. And the way to diminish the pain that I found that worked was to immerse myself in an imaginary world. And so that was the driver at that point. But when I got to college, I realized that same tool that I had used to avoid the pain of the loss of a mother was a tool that I could harness to do physics with. And so, yes, these pictures I saw, for me, although they were static in the book, I could see the motions that I'm now able to illustrate for you with these computer graphics. These are images of what light has a property called polarization, which says that it behaves like a spinning top, but it can spin in a counterclockwise sense or a clockwise sense, and that's what you're seeing on the screen here. And I could see these things in my head as I was reading the books with the names of Michael Faraday in them. So I'm going to talk about a 205 encounter with Michael because after I left college, well, let's see, 1969, I was a freshman, got my 2 bachelor's degrees. Thank you very much for mentioning, Mark, in the introduction, one in math and one in physics in 1973. I stayed at MIT, and in 1977, I got my PhD in physics. I'm the first member of my family to go to college. It had always been a dream of my father that though he did not have a chance to go to college, that his children would have such an opportunity. And since he knew that at age 4, I told him I wanted to grow up to be a scientist. At age 14, I told him about this school where I thought they only made you study the good stuff. For me, the good stuff is by definition math and physics. So for him to see his son, who voiced these dreams coming up as a child, walk across a stage in 1977 to receive a PhD, was a triumph for our family. So let's fast forward for like almost 30 years, 25 years. And can we have the lights up just for a bit? Is that possible? Because one of the things that excites me so much about tonight is to be here in this temple of science that rests to a large degree on the work of Michael Faraday. There's a wonderful museum here that I don't know if you've all been down to it, but I have, and I had a tour guide tonight, and that's when I turned fanboy. Just walking through that space and watching that and watching experiments, and now we've had a recreation of the experiment. So this little apparatus that you see here is, in fact, one of those tools. And it's in fact one that we just saw. So I wanted to, I'm a theorist, by the way. So if it doesn't work, it's not the device, it's me. So let's see what happens here. Let's try this again. And so it's absolutely, like I said, amazing to me to be here tonight delivering this presentation and talk to you, because it connects to my life over a period of several decades. This video that you saw was from a film called Einstein's Big Idea. The producer of that film is a gentleman by the name of Gary Johnstone. Gary, are you here tonight? Did you make it? I guess not. But that clip that I just showed you came from my having a conversation with him about a week ago, because the film is actually much longer than the part that you saw. But to have this kind of interaction with the Faraday spend my life decades apart, and now coming here tonight as a continuation of this story, was something that I wanted to make sure that I shared with this audience. So we can have the lights down now, please. There we go. So, Michael Faraday was the avatar for another great physicist, James Clerk Maxwell, who in fact essentially took everything that had been known and discovered about how magnets and electricity work, and he put it into this one tome, this one book. Now, of course, we talked about Isaac Newton earlier, and there's a book called the Principia that Newton actually starts physics off with. I mean, before that, there was natural science. After the Principia, there was physics. These are two different things, and Newton is the person responsible for that. And part of that responsibility was because his ability, his mathematical ability, allowed him to create a subject that students just love to study in school called calculus. Oh, I guess they don't love it so much. But like Newton, Maxwell did the same thing for electricity and magnetism. He wrote this book, a treatise. The initial notes from historical records show that he kind of got all the answers together in the 1850s or 60s, but the tome was not released 10 or 15 years later. It's Maxwell's treatise on electricity and magnetism. And so one of the things that allowed Maxwell to complete his work was it rested on the foundation of the work done by Michael Faraday in this institution. So Faraday was an experimentalist, and who conveyed his ideas in clear and simple language, which I'm attempting to do tonight. His mathematical abilities did not extend even as far as trigonometry, and were limited to the simplest of algebra. James Clerk Maxwell took the work of Faraday and others and then summarized it in a set of 4 equations that we now call the Maxwell equations, and they are the basis of everything that our species has ever studied about how electricity and magnetism work. On Faraday's use of lines of force, Maxwell wrote the following. He said, "They show that Faraday to have been, and in reality, a mathematician of a very high order, one from whom the mathematicians of the future may derive valuable and fertile methods." And that's really what we're about here tonight, is to build on that use of the idea of lines of force. You see, at the time that Maxwell and Faraday were doing this, is post-Newton, so when you talk to scientists, they were thinking about forces that basically were pushes and pulls. But what Faraday does is teach us that the universe has more to it than those things that we can see pushing and pulling in life. And these things that we are not able to see are just as real as the things that we can see. And these lines of force are an illustration of that idea. So under Faraday's impact, the definition of physics expands suddenly, because before that it's pushing and pulling and pulleys and weights, but now it's those things plus these invisible influences. And that is a monumental idea. Not just invisible, but influences that have an impact on reality, which is actually very different. So here's a cartoon I created. Well, we'll come to this shortly. This is a cartoon that I had created to get to one of the essential ideas that drives Faraday. In the center of this, you see a little white dot, and it's moving, it's jiggling up and down. And then you see a bunch of green lines coming out from that. Those are illustrations of Faraday's lines of force. So we can see them in this computer this computer animation, what he was seeing in his head. And so you can see that as I jiggle the charge, the lines of force start to undulate. And they undulate, and you can see that you get these wave-like structures coming out. Those wave-like structures have a name. They're called photons, because that's what photons are. They're kinks in the electrical lines of force that Faraday introduces into our concepts of physics. Here are Maxwell's equations. There are 4 of them. The first 1, 2, 3, 4. The conservation of charge is a consequence of those first 4 equations, and the Lorentz force law is not a consequence. It's something very different. The Lorentz force law tells us how these invisible influences have an impact on material objects. And so remember, I said they're invisible, but they have an impact. You have to be able to state that impact mathematically. That's what the Lorentz force law does for you. So I just showed you some math. Some of you may be a little queasy. But instead of allowing you to take a break to recover your calm nature, we're going to instead consider the following. I'm showing you now a score. A score of a piece of music that I actually love. I don't know how many of you know Rachmaninoff's Second. If you know the film Brief Encounter with a wonderful actress, this piece of music is all throughout that. And so I commend you, if you want to see good music, great music, and a great story, go look for Brief Encounter. It's on YouTube. You don't have to pay even a single shilling to see it. But the reason I brought this here is because to remind you of something. No one in this audience, I think, feels nervous when you see that. But on the previous slide, where we had those equation things, it might have been a sense of queasiness. So why is that? Well, my claim is that these things are just as complicated as looking at equations. So why don't they make us nervous? I believe part of the reason is because as humans, those of us who can hear, we have direct access to the concepts that sit behind these scores, the music that is played. So we have an intimate connection to these complicated symbols. It doesn't worry us. On the other hand, when I show you a piece of mathematics, for people like me and Maxwell and a number of us who call ourselves theoretical physicists and people who study physics deeply, those are musical scores. They're just musical scores for us. And so I'm trying to get you to the point of saying, well, I may not know that music in detail, but it's really no more difficult than thinking about a musical score. And the thing that about the math that we do is, so you might ask, well, if those are musical scores, what's the music they're playing? It's the computer animations I'm showing you. Because with computers, I can show you what that music is. And for people like Faraday and Maxwell and all of us who do this stuff, when we see these equations, we can see the story behind them. That's the secret. That's our superpower. So Faraday's lines of force and why the photon looks like a starfish in a ring. I wanted to explain that to you since that was a question I asked. So that was a picture we saw, and I asked if anyone had seen it, and I think most of you said no. But it is on the web if you go look. The web is, after all, the font of wisdom and truth these days, right? So, as I said, the clips I showed were from Gary's film, Einstein's Big Idea. And there's a scene in the video where Maxwell and Faraday are talking. By this time, Faraday's an old elderly gentleman. Maxwell's still in his prime. And Maxwell says to Faraday, this electricity producing magnetism and magnetism producing electricity can only happen at a very particular speed. The equations are very clear about it. They come up with just one number, 670 million miles per hour. It's the speed of light. That is the speed of light. You were right all along, because you see when Faraday came up with these concepts, he also came to the conclusion that what he was talking about, this piece of electricity creating a piece of magnetism creating electricity and oscillating back and forth, he asserted that must be light. It took him 15 years to convince the establishment that he was right. And that only happened after Maxwell was able to derive these results from an equation. Okay, so here is, again, some of that math stuff. Remember, it's just a score, so don't get nervous. The pictures that you see above is the music that's the score below is actually describing. So here's our picture that the scientists in Birmingham, which I understand is right next door, took a few months ago, last summer actually, of a photon. Now let me talk about how they did this. They used what's called a quantum mechanical device. You've probably heard the word quantum because it's all over society, quantum computing, quantum information. It's a buzzword. It's got to be a buzzword in the world societies. And so they were using a device that took advantage of that piece of science, and they used it to image data about a photon. And then an artist took that data and created this picture that you see. So you could imagine going back in time to the time of Maxwell and Faraday and showing this picture. My claim is this would be the response. What? I work as a starfish in rings? Really? So, like I said, when I first saw the picture, I was like, wait a minute, why does that ring a bell with me? So I thought for a little while. Because when you look at most books, that's what you see as a picture of a wave. And here I've illustrated the electrical field for you in the lower section of this. That's what you see in books. But we've got these scores. So if you're a musician or you study music, you're used to the idea of a variation on a musical score. That is, one person writes a piece of music, another person comes along, they change some things about the timing, maybe some of the notes and what have you, and they have a variation on an original piece of work. So this score that I'm showing you here is the standard score that you will find in generations of textbooks talking about light. And in fact, I saw these kinds of equations in that 1970 first encounter with Michael Faraday. That sure doesn't look like a bunch of starfish and rings. So I, in 2004, was looking at this, having no idea someone was going to actually image a photon, and said, what else could you do with that initial score? And I decided to write a variation. This was in a project called Superstring Theory, the DNA of Reality, which is a project that I was involved in creating. And I had a young person assisting me. And so let's go back and try to explain why this comes out this way. First of all, when light actually hits something, it causes motion. If you could actually take a photon and shoot it at a particular electron in an atom, that electron would start to move. It's the reverse of what we see here, where the moving electron creates the light. If you do it in reverse, the light causes the electron to move. So the quantum mechanical device is one where you can measure these motions of electrons. That's the first thing. So when I did this variational theme, I came up with this picture that you see here. I did a variation of mathematics that's in standard textbook, and I said, well, what you get after that variation, which, by the way, for those of you who are scientists, what I did is a change of coordinates. I went from what we call rectangular coordinates to cylindrical coordinates. And if you take that standard variation, make this change of frame, you get this. And then I went to a computer graphics kid, and he turned my equations of variation into this. Now, in this, we're going to talk about for a second. In this, I want you to imagine that you're in a spaceship somewhere, and someone tells you, I'm going to shine a light beam past you. I want you to fly through the light beam. And I want you to fly right through it and tell me what you see. So here we're going to enter the light beam. Let me see if I can back it up. Let me just stop it for a second. This, that's what you see when you enter this variational theme of a standard formula that's in a textbook. And you can see there are rings and starfish there. So after not so much thought, I said, of course it will look like rings and starfish, because I did this 10 years ago. But this story illustrates the power that mathematics conveys on us who can see the stories that sit behind the mathematics. We can figure out what things are going to look like, in this case, 10 years before we have the technology to actually do that. Okay, so let's continue. Here's another, this is my, I call him my hero Maximus of physics, Albert Einstein. I was introduced to Albert Einstein's work at the age of 16 when I took my first physics class. I had a fantastic physics teacher named Mr. Freeman Coney, and he actually introduced us to special relativity. Now, special relativity is actually part one of a two-part story. So we're going to jump ahead. So that comes from a 1995 film called Breakthrough, The Changing Face of Science in America. And it was the first video that I agreed to appear in. So that's Jim Gates in 1995, on a train in Siberia, with a picture of his children in front of him, if you've noticed, who were just 14 months old at the time. So that's when I began to learn how to do what I'm doing right now. Because before that, I was severely, severely shy, and Mark will tell you that I was pacing back and forth as I was preparing to come out and speak to you tonight, because this is what I do. I'm always nervous about speaking to audiences. So this film, in the part of physics, there are four of us that appear in it. There is a gentleman who's a computer scientist named George Castro. There is a space scientist by the name of Franz Cordova. Franz, by the way, just 2 years ago, stepped down from being the director of the United States National Science Foundation. And then there was this other guy, I have a really hard time remembering his name. It's Neil deGrasse something or other. So this was also Neil's first video, and there are thousands by now, but this is the first time he stepped in front of a camera. He's another part of the story. So in my part of the story, I concentrated on Einstein's gravity because that's where we're going next. So again, I remind you, it's a score, folks, but it's going to be a math score. So this is what Einstein's math score begins to look like. It's a bunch of equations that define some objects that, if you're a PhD or during your PhD, it will make sense to you. If you're not, just think of it as a math score. Here's some more of it. You'll notice I say it part 2 because the first part of the story is the one that you know about very well, namely that as you go faster and faster, things seem to shrink, time seems to slow down. That's part 1 of the Einstein story. But this is the part 2, which is not so widely discussed. So it has inspired some science, a spectacular science for our species, namely his equations, just like Maxwell's equations, describe waves. In the case of Maxwell, those waves are what we see if they're in a particular crest-to-crest distance. As you change the crest-to-crest distance of these waves, you change the color that we perceive. And there are distances that we can't see at all because they're either too long or too short. And one of the interesting things about life on our planet is that we know there are certain shrimp that can see more colors than we can because they can see a wider range of these wavelengths than the human eye perceives. So Einstein predicts waves. In 1985, I was an advisor on an advisory board to the National Science Foundation. And there was a program officer there by the name of Rick Isaacson who called me into his office and said, "Jim, I want to show you something." And he showed me a proposal to get some research done. The proposal came from scientists at Caltech and MIT. And when I looked at it, I said, they're crazy. It was a proposal to measure the waves of gravity that Einstein had predicted that no one had ever seen at that time. So thank God Rick didn't listen to me. Because Rick Isaacson, who's not so widely known, is in the U.S. Science Foundation. He's the person that pushed LIGO from this proposal to its great success in 2014 when, for the first time, humanity was able to measure these gravitational waves that Einstein's equations had predicted around 1930. So I'm going to take you to LIGO a little bit. These waves are produced when, for example, two black holes coalesce. So black holes sometimes meet each other and build a bigger black hole. Here we have a cartoon illustrating that. And these waves that you see here are the gravitational waves. They, just like light generates signals, these gravitational waves generate signals, but you have to have a device to detect them because like the light that's outside our frequency range, you can't see it. But we can build devices, instrumentalities for this purpose. So this cartoon showed us two black holes getting together, generating a set of waves, and then these waves have traveled to, at the end of it, to planet Earth, where we have devices to measure them. The actual devices that do that are called LIGO, the Laser Interferometry Gravitational Wave Observatory, and I've had the pleasure to be involved as an advisor, not doing the science, but advisor to LIGO on a number of occasions. And so I've watched it as it came from a piece of paper to a piece of reality, creating earth-breaking science. It's large L-shaped. If you go there, it's like looking at two large-shaped tunnels, which you can see sort of illustrated in the first two of these pictures. The length of these tunnels is about 2.4 kilometers, if I remember correctly, each way. And inside of them, you use lasers to detect these gravitational waves as they hit the device. Three gentlemen won a Nobel Prize for this work. Barry Barish, Kip Thorne, and Ray Weiss. I met Ray when I was a graduate student at MIT. He didn't quite teach me, but we had some discussions together. And Kip Thorne was a professor at Caltech, and we're going to come there. And these gravitational waves, remember the winding motions that we saw for light, that it had two kinds of winding motions? These gravitational waves, mathematically, are predicted to also have these two kinds of modes, as we call them. And Interestingly enough, someone at YouTube actually created this. I mean, I have no idea when or why these videos were created, but they're the most accessible description of gravity polarization that I know exists right now in the media. And so I obviously borrowed them and made reference to where I found them. And so just like our light could wind around in a right-handed sense or a left-handed sense, these gravity waves can do so. What do they illustrate? Well, what you imagine is that you're looking down a tunnel, a perfectly circular tunnel, and that there's a gravity wave approaching you from the back of that tunnel. And as it approaches you, it deforms the walls of that tunnel. And in principle, that's something you ought to be able to measure. And so you see, even though we know gravity waves exist because of LIGO, this is a measurement that we have not yet done. So that's the next big challenge for LIGO, to figure out if we can measure these polarization states of the graviton. So you can have positive helicity, or you can have negative helicity. Now, we keep moving. So I got to take you into quantum mechanics now. And Richard Feynman, who was certainly one of the world's greatest physicists after Einstein, I had the great pleasure to be a postdoc in his research group from 1980 to 1982. That group was co-led by Murray Gell-Mann, another giant in physics. So you can see, I got a chance to hang out with some like big shots. But Richard Feynman once said, nobody understands quantum mechanics. And I'm sure you've seen all kinds of things where people try to get you to say, oh, it's like this, it's like that. I'm going to give you another way tonight. I hope I'm a bit more successful than most of the things I've seen before up to this point. So we're going to I don't know if you can read this title, but my question is the quantum vacuum the result of Macbeth's witches' brew? Right? Remember the story of Macbeth and bubble, bubble, and toil and trouble, right? And so they had a large cauldron in that story, and I'm going to use that cauldron to try to, in your mind's eye, create a picture of what we mean by the quantum vacuum. Okay, so here's a picture of Richard Feynman. And he looked like that so I was there from 80 to 82, so he looked pretty much like that. This is me in 82. And I'll never forget the first time I had a conversation with Richard Feynman, and I'm going to relay that story. So we were taken to lunch at a Chinese food restaurant, because that's what happened when the semester began, when the new kids came to town. And I'm sitting around a table, and Richard Feynman is about the distance I am from Mark Richards right now. And I look over there, and I've been reading about this guy for over a decade, all through the time I was at MIT. Richard Feynman. I mean, we knew him as the new Einstein. So I'm sitting there, and Feynman is talking and having a good time, and there's a conversation going on. And I'm sitting there thinking, if I say something, he'll figure out I'm an idiot. Under those circumstances, the best thing to do is not to say anything. So I'm shaking my head and smiling. And then finally, he figures out what I'm doing and confronts me on it. He says, Mr. Gates, that's your name, isn't it? I said, yes, Professor Feynman. He said, you know, when I was your age, I wanted to wear my hair just like that. That blew my mind for a second, because I could see an image of Richard Feynman with an afro. I was never afraid to talk to him again. This shows a level of emotional intelligence on his part to understand the turmoil that was going on within me, and then finding a remedy to open a bridge so I could talk to him. And that's amazing. So he was one of my mentors, and here's that cauldron. Okay, so we imagine going back out on, maybe we're out in Ireland or Scotland someplace, and it's a cold night, and there's a big cauldron out there. We decide to put some liquid in it, but we don't light the fire. So the liquid provides a perfectly pacific and quiescent surface. And since I'm kind of a demented witch, I'm going to put a little toy boat on the surface and give it a push. So I'm going to use my cursor here to imagine that toy boat, and I give it a push. And if there was no friction, what's going to happen to this boat as it moves along? What did Sir Isaac tell us about that situation? It's going to move at a constant speed in the same direction. That's Newton's first law. And here, we could see it demonstrated in principle if we could eliminate friction. Now, let's imagine the witches come along and say, get out of here, Jim. We want to start our fire. And they start a fire on the cauldron. And so the surface of the cauldron begins to bubble. Now, I come back and say, can I play my game again? And so I decide to put my little boat here, and I push it into the cauldron. Does it move in a straight line? No, because the bubbles are going to be constantly pushing it left and right. And so I no longer see Newton's law emerging. Instead, I see something far more complicated, trying to understand the motion of my ship as it moves across the surface of this boiling cauldron. And so I've got to throw out Newton's equations because they're not applying here. I've got to find some new equations. And for our species, that happened around 1905. A physicist named Bohr, was looking at the experimental results that were coming out of looking at how electrons behave. And the first thing they discover is that they don't obey Newton's laws. So that's just like saying you got this bubbling surface of a cauldron. And then they have to figure out an equation. So Bohr gives a result, but its story is finally settled in 1925 when Schrödinger writes his famous equation for quantum mechanics. And in fact, this story I've told you, both the fanciful part and the real part of it, in my mind has raised a very interesting question. So if there are any physicists in the audience, I would propose a question to you as a serious research subject. Namely, are there classical systems that can simulate the laws of quantum mechanics? Because the thing that I have just described for you is a classical system. It's just water in a pot, and I'm boiling it. And I'm asking, what's the motion of a particle that across the surface of this boiling object? And I don't know the answer, and I don't know that anyone has ever thought to ask this question in this way. And that's why it's a research problem. So anyhow, this is sort of what the new equations look like. This is not a complete rendition, but this is part of the mathematics of the Schrödinger equation. This is the new score. And you can apply this score, it turns out, to lots of things, not just electrons, but in fact, there are four forces in nature that we've measured. There's gravity, there's a weak nuclear force, a strong nuclear force, and electromagnetism. And this little cartoon here illustrates the force. The gravity keeps us orbiting around the sun. If you take a neutron and could isolate a neutron and just hold it there, after a few minutes, you would find you were holding a proton. Because neutrons that are outside of the nucleus of the atom decay. And so they become transformers. They change their identity. Now, in this transformation of identity, they turn into protons, but they also spit out an electron. That's to balance the charge, because beginning there was no charge. Now you got a plus charge and a minus charge. And they spit also out a particle called a neutrino. By the way, that's where I kind of really do my stuff, is looking at the mathematics around those things. The strong nuclear force is also easy to understand because that's the source of energy from the sun. It's a nuclear reaction. It's not the same as beta decay, which is what we call this first process. And it is the source where basically you need to have 4 hydrogen atoms joined together to form a helium nucleus. And when you do that, you get a bit of excess energy out, and that's the source of the sun's energy. And this over here is electromagnetism, so I won't spend time. So when we think about our boiling cauldron, it turns out the mathematics that we know how to describe these boiling cauldron analogy systems, they work if we're looking at the weak nuclear force. They work if we're looking at the electromagnetic force. They work if we look at the strong nuclear force, although it's a little bit complicated. They totally break down for the gravitational force. By the way, for those people who don't like these kinds of things, I like to point out this is the best tested piece of science our species has ever created. This is a piece of science that if you measure it and then do the mathematical calculations, they agree to more than 1 part in a billion. So that's why people like me are convinced that quantum mechanics is real. It's not something fanciful. It's something you can measure the effects. So, next in this, we're going to go to 1980. And we're going to meet the wizard at Trinity Hall in Cambridge, England. For those of you who can't figure out who that is, it's this gentleman. So in 1980, Stephen Hawking was interested in the problem that I just told you about. He wanted to understand gravity, but he wanted to understand it in such a way that is consistent with this boiling cauldron analogy that I've used. He wanted to understand quantum gravity, and that's what quantum gravity is. It's the combining of these two different pictures in a mathematically consistent way. And Stephen was interested in this for even back in 1980. And that's the problem, by the way, he spent the remainder of his life working on. So, when you're an old person, and Stephen wasn't super old, but when you're an old person, it's usually a good idea to not talk to your friends because they're old like you. And they think the same thoughts you're thinking. So you might want to gather a group of young people around you. And so in 1980, there was a conference at Cambridge called the Nuffield Conference. And he invited young people who were working on this new piece of mathematics that had just been created within the last decade before this meeting called supergravity. Now, if you look at this picture, this is our conference photo, and there's one kid in there with a really good tan. And that would be me. Because by this time, this is 1980, this is 3 years after I got my PhD, I wrote MIT's first thesis on a subject that is related to what Stephen was asking. And that's how I got invited to this conference. It's really weird to write this thesis, by the way, because no one at MIT knew anything else about the subject that I was working on. I'm a graduate student saying this is going to be important for the future, and I just went to work on it. So, now we're going to come back to Richard Feynman, because Richard Feynman is in some sense, is the Zeus of this idea of the quantum vacuum. He's the person who's pushing it. And so here we see a picture of Richard Feynman and animation for this quantum vacuum concept, which you can think about as the surface of a boiling cauldron. And we want to know this, for example, around these gravity waves I talked about sometimes are generated not by black holes, but by neutron stars. So we see a cartoon on the left-hand side of this image showing a neutron star pair. So how does the boiling cauldron affect the signals that we would see from such objects? That's a question that would be important if you're going to try to observe these things. And so Richard Feynman keeps pushing us and pushing us. There's one other person I'm going to bring into this story because so Stephen was never successful in his quest for this unification between classical gravitation and quantum physics. In 1995, this guy, a guy named Edward Witten, for my generation, we consider him our smartest physicist. Now, most people have never heard of Ed because you hear about Brian Cox or Brian Greene or Neil deGrasse Tyson, and a list of other people who are absolutely brilliant at what they do, which is to talk about physics for the general public so that you can have some confidence that we're not just wasting your money. But Ed, for most of his career, has been rather cloistered. Recently, he's come out and done a few podcasts, but he's our generation's Einstein. So in 1995, he proposed a mathematical solution to the problem that Hawking was not able to solve. He called it M theory. Now, M theory is actually part of string theory, and I know that a lot of people think string theory is dead. That's just fake news. And if you want to know why it's fake news, I can talk to you at length after this, because it would take too long for my presentation. And so this M theory combines all the equations of string theory, and it combines with one other thing called 11-dimensional supergravity, and then that sets up a 40-year-old problem. Is Ed's suggestion consistent with Feynman? And the answer turns out to be no. He's got a set of equations. They're not actually consistent with Feynman's view of quantum mechanics. And so, like most people, when confronted with a hard problem, we physicists say, retreat. Because we do. We don't solve the problem collectively. It's considered a dead area. For example, even gravitation was considered a dead area when I was in graduate school. And now we've seen gravity waves and all of these developments of neutron stars and corrections to the Big Bang. So when physicists run away from something just because it's hard, the pattern is a couple of generations down the road, the hard problems get addressed. So there's this problem. And one of my mentors back in from 77 to 1980 was Abdus Salam. Abdus Salam of Imperial College, right here in London. I met Abdus in 1977 the first time, because Abdus was the creator of a physics center in Italy called the International Center for Theoretical Physics. And I was invited to give a lecture there. And just like you're sitting here, about the distance where this young lady is, I was lecturing, and there was Abdus Salam. And so the butterflies started. There's Abdus Salam. He's going to figure out you're an idiot. And so I got to my lecture. I didn't have any major gaffes. And then, to my surprise, he invited me to his office. So I went up to his office, which has a beautiful, the center actually overlooks the Adriatic. And so you have a beautiful view of this sea sitting out of his third-story office window. And I'm sitting there. And he says, well, look, I'm paraphrasing. I don't have a recorder here, but I'm paraphrasing the conversation. He said, I didn't know that you were a black man. I sat there. And I didn't say, but I thought, that's because I don't write in Ebonics. I don't write in slang. I write in mathematics. So how would you know, right? Then the next thing he says to me totally puzzles me. He says, and again, these are not exact quotes, but this is the sentiment. He says, it was his belief that when a sufficient number of people of the African diaspora enter physics, something like jazz is going to appear. Now, when he said this, I'm thinking, what the devil is this guy talking about? It took me several decades to figure that out, but eventually I did. And in fact, that expression, that something like jazz will appear, has been translated to one of the young people I've been talking to named Stefan Alexander, who I believe has been a lecturer previously here. Is that correct? Not yet, but is coming? Maybe, who knows? He wrote a book several years called The Jazz of Physics on the basis of those stories that I told him. So some of you might be aware of that book. So anyhow, Abdus, like all of us, we're really writing scores, folks, but it looks like this. So Abdus wrote a score that Ed is supposed to be consistent with Ed's prediction or assertion that he has a quantum gravity theory. And Abdus' score looks like this. But then Richard Feynman has a certain view that Ed's picture is not consistent with. And no one knows how to solve this. And so let me jump ahead a little bit. Witten has given us these symbols, some mathematical functions, notes. That's the way to think of it. These are notes, different kinds of notes. And Richard Feynman is saying, where's the rest of the story? Because there has to be a rest of the story to be consistent with his view of quantum mechanics. So in order to answer that, I'm going to show you a little bit about our universe. Namely, in our universe, we know about electrons. We know about particles called muons, which are copies of the electron, but they're 200 times more massive. We know about other particles called tau particles, which are copies of the electron, but they are 1,700 times more massive. So these are things that we have, in the last several decades, observed in the laboratory. So we know these other things are there. There are other objects called neutrinos. Each of these copies of the electron also bring a copy of a particle that is like an electron, except it has no charge, and it's very much lighter than the electron. So all of these objects I've collected together in this part of this table that you're seeing here. Now, inside of protons and neutrons, there are these things we call quarks. And so it turns out there are 6 varieties of quarks. That's what you see in this part of this table. The other things that you need in your basement to construct a universe, in addition to these things, are particles that carry forces. The photon carries the electromagnetic force. Remember, that was only one of 4 forces. So have to be carriers for the weak nuclear force. It turns out there are 3 of them. There have to be carriers for the strong nuclear force. It turns out there are 8 of them. And these things have been observed. Their implications have been observed in experiments. So I'm not just telling you about mathematics. So that's what our universe looks like. Does that look like a very balanced table to you? In my life, as I've asked this question, I've had a few individuals say yes. And I've always thought, let me get your name and number, because I have some people I think could help you. But most of you said no, and that's sort of the standard answer. And the reason is because we humans are actually coded for symmetry, it seems. Even our notion of beauty, it seems that we judge beauty in people's faces by how symmetrical those faces are. So using that standard of beauty, I have a little puzzle for you. Think of each of these balls as a box. So how many boxes do I have in this upper quadrant here? 5. Okay, now let me ask you this question. If I wanted to have a symmetrical, balanced picture here, how many more boxes would I add? 3, right? And then it would be 4 on one side, 4 on the other. Let's do the same thing down here. Here I have 24 boxes. This box is empty. How many new boxes do I have to put there? 24. And now, having created symmetrical here, I want this to be symmetrical with that. So what do I need over here? 8 more. So on this principle of beautiful balance, you would say, well, Professor Gates, the thing you're showing me isn't very pretty, is not balanced, but my aesthetic sense tells me that if I add some more boxes, I can get this. These extra things that we're adding here are called super partners. They are supposed to be forms of matter and energy that we've never measured in the laboratory, but they bring this symmetry to the organization of what there is in nature. And if you actually look at the history of symmetry in this connection, if you look at Mendeleev's first chemical table of elements and compare it to the table of elements we have now, the first one is very asymmetrical. So symmetry has been a wonderful gift to us as a species in figuring out things. So this is what is called supersymmetry. And opposite equations guarantees that you always have this balance in all equations that you write. In 2010, I think it was, Physics World was kind enough to give my research group its cover page because we have figured out how to take those mathematical scores and convert them into pictures. And then by manipulating the pictures, study the mathematics. So this is how it's sort of done from the point of view of mathematics. You start with here, I'm starting with a hypercube. I decorate it with open and closed nodes. I put a bunch of colors in and dash lines. This thing here is actually a set of equations. And these equations have that balance property that Abdus' equations have. Here are more equations. And so now this picture-making process that I described, that I created with Michael Fox in 2004, converts to these 3 pictures. So we know how to take pretty complicated differential equations, partial differential equations in the vernacular of my community, and convert them into visual images. And so this is the opposite of what Michael is doing. Because remember, Michael is actually looking at physical reality and figuring out the images that explain what's going on. So it's the reverse process. But you can do that. That's what Richard Feynman did in creating his so-called Feynman diagrams. So in 2020, working with 2 graduate students at Brown University, I decided that, well, I'm sufficiently old now. I'm 20, let's see, this is 2020, so I'm 70 years old. I don't care if people think I'm crazy. I'm going to attack this problem that no one else has solved, which is to try to get this balance in the Witten problem. And working with these 2 young women, Young-Gray Hugh and Hazel Mock, we wrote a series of papers that first thing we did is convert the equations in Witten's formulation into pictures. And that's what you see in the upper half of this diagram. And then after we learned how to do that, we asked, can we get pictures from Abdus' equations? And it turns out you can. Now, this mathematics even defeats me to explain what it is to an audience like this. In fact, it defeats me even to explain to most mathematicians. But we found a mathematical object that generates every possible picture associated with Salam's approach. And so what we did, because we now have these pictures, instead of trying to solve equations, what we did is we're going to give you this big library of pictures. We're going to give you the list of pictures that Witten gives us. Can you find us the book in the library where these images occur? So we're literally teaching the computer how to look at our images, not the equations not the equations that give rise to the images. And the answer is yes, we could. The object turns out to look like a chandelier. It's got 4 billion parts in it. And that's why you need computers, folks. Because even I can't spend my life writing down 4 billion terms. And this chandelier was constructed from that thing that I can't explain to people about, but it's a bunch of mathematical rules. And we found it's a little like CSI. Those 3 Witten images are like the fingerprints of the crime scene, and the big chandelier is like the background where you're trying to match the fingerprints to what's there. And we found it. So we were able to solve this problem that had been around for 40 years by throwing mathematics out of the window, going to the use of visualization, teaching a computer how to visualize these images, and then asking it to do a matching for us. And so we now know how to invert that process to find the mathematical functions that augment Witten's construction. And so this is the possibility, leads to a possibility of a new type of laws of physics. So in the process of developing these things with my students, there had been a decade of work, and what we found is that these pictures, which you see here, are manipulable. Namely, if you do things to these pictures, you're actually doing things to the mathematical equations, and it's what the mathematicians call a morphism. We found a morphism. And so I'm going to, in this morphism, since I think I'm running short, so when I'm moving things horizontally, in math language, I'm multiplying by matrices, for those of you who know such things. So I'm going to do a series of matrix multiplications on this image. That's what you're watching here. The next thing I'm going to do is a little bit of calculus. And since I'm doing everything visually, calculus has got to be some kind of visual thing. I just did it. I just integrated a function. That was that lowering of that upper node. And now I'm going to do lots of integrals. So now I'm lowering those. And now one more time. And now you can see, let me stop the film here. Now you can see there's something very peculiar. That image that I started with didn't look like there were copies of anything. It looked like everything was just very, very different. But by these manipulations using integrals and matrix multiplication, what I can detect is that there are actually subpieces of this object that are identical to each other. And you can go a bit further and say, well, are you really looking at two things, or are you looking at an object in its mirror reflection? And that's a question that has a mathematical instantiation. And so we studied that, and it turns out the answer is yes. I'm sorry, I didn't mean to skip the film there. Let me see if I can get the image I want. When you let this process all run of these squishing together, you get this image. And so one of the questions was, can you just match in any kind of way, or is there a particular kind of way that you can match? And the answer turns out there's only one way that works, and this way that works corresponds to what computer scientists call error correcting codes, classical error correcting codes. So, because of the research effort I've led over the course of the last 20 years, this is an example of a type of, we don't know that this is our universe yet, because you have to actually measure those balanced particles to know that. But if those balanced particles are measured, we will assert that for the first time, laws of physics depend on classical error correcting codes of a type that we humans have invented for computer science. No law in physics that I know about ever has made this assertion. And so, for me personally, the gift that Michael Faraday has rendered to me was allow me to find the first example of this phenomena. And if nature's kind to us, I wrote an article in 2006 that said kind might be 100 years, which means I'm not going to be here. But if nature's kind to us, then we would have discovered a new law of physics. And that's what Michael Faraday did for me. I'd like to acknowledge the visualizations. As I said, they came from this video course, which is still available, called Superstring Theory, the DNA of Reality. I have lots and lots of people acknowledge, my graduate students, my postdocs, my collaborators, and I'm done.